14. Hi, Gavin. We're grading. Sorry. Okay, we are on 6B. Abby says, hello, my dudes. I'm not sure I could catch you or pick you up. We're on 6B, and we're trying to eliminate the parameter y equals x squared is a valid equation eliminating the parameter of the whole graph, but the path is only from 0, 0 to negative infinity, right? So, could you have put y equals x squared, comma, for x less than or equal to 0? Yes, and that would have been just that part of the graph, right? But what did they do instead of saying y equals x squared for x less than or equal to 0? They solved for x, because solving for x splits this up into a plus or minus root y, which splits this up into 2 branches. And so what they had to figure out, is it the positive branch, or is it the negative branch? Well, I needed the negative x's, I needed the negative infinity x's, so it's the negative root. Because the positive root would have been the positive x's going the positive way.
Because I was thinking like when you transpire, like trying to eliminate the parameter, you like divide by negative 1 both sides.
Oh yeah, but that negative disappears because of the square. So actually this has nothing to do with that.
Okay.
Does that make sense? Yeah. So the negative squared turned into a positive, so that's good. But then they said, hey, I can split this curve up by square rooting both sides and putting it in like a, sort of like an inverse notation. So what they did is just split it up that way. But if you guys had said x less than or equal to 0 or x within negative infinity to 0, that also gives you the proper branch. Number 14, you guys are graphing as well. The orientation should have been clockwise. Initial and terminal point are the exact same thing of 0, 5 on, I think they gave you 0 to 2 pi as your period, right?
Yeah.
Or as your domain. Okay. Eliminating the parameter, you guys ended up with, theoretically, x over 4 squared plus y over 5 squared equals 1, because it was an ellipse with a minor radius of 4 and major radius of 5. Number 20. Initial point 0, 2, terminal point 4, 0. Orientation is clockwise again. The parameterized curve traces. Now this time they didn't make it all crazy and try to like solve for x or anything else. They just said, okay, whatever. It's this, but it's this for x greater than or equal to 0. So it kind of helps that out. And this curve doesn't keep going, so we don't have to worry about x being something higher because the domain restriction is naturally stopping the x at 4 anyway. Number 30 is in quadrant 2, 32 is in quadrant 4. And 38 is true. Oh, okay, and we're done with the evens. All right, cool kids, I'm ready. What stuff do you want to see? I don't think I'm going to get people up to the boards on this section because polar and parametric is not something that you guys are necessarily just briefly reviewing. A lot of you are having to think about it. Is there anything in the homework that you want to talk about? Evens or odds? If you didn't grade your odds, you can go back and look at it real quick. See if anything's posing any problems. Oh wait, are we good? You guys are good? You sure? If you're not good, you're going to let me know. Did we understand 30 and 32? Because they're really weird answers.
At first, I thought it was like, there's a table
Uh-huh.
for 29 to 32, and like, just like, doing the table, I thought it was the in between negative 5 and negative 3.
For number 30?
Yeah.
Uh-oh, off the line axis. That's not good.
I might have done my table wrong.
We can peek real fast because that actually is a valid way of doing it, and I'm not entirely completely convinced that everyone in this room knew exactly how to do 29 through 32 because it was kind of confusing. Unless you did a table. For all of those, oh, sorry, your screen is frozen. For 29 through 32, you're given a graph, but a graph without, oh no, you do have equations up above. and you were trying to figure out the domain restrictions or the intervals for the t's that would get you in the first, second, third, fourth quadrant, right? So AJ, when you made your table, what kind of values were you plugging in?
Like at the top I had t and then for negative 5, and then I plugged in t.
Yeah, I think that's exactly what I would have done too.
So then, for like when I put negative 5 to negative 3, the x values were from negative 2 to 0 instead of 0 to negative 3. Because like on the table, it's like starting from negative 2, then goes, then like it kind of like reverts back.
Yeah.
It starts at negative, like the interval starts at negative 2 and ends at negative 2.
So 3 minus 5 would be a negative 2. I see that. And then y would be a negative 6, which is third quadrant, right?
Yeah.
Negative 3 would be 0. 3 would be 0. Negative 3 minus 1, negative 4. 3 minus 1 is 2. 0 is 3. I'm just throwing these in because I saw 5s and 3s in the answer, so I'm just kind of cheating. But I probably would have done more also with negative 4 and negative 2 and negative 1. Nope, sorry, 0 minus 3. Minus 1. Okay. So just peeking real quick and not having tons and tons and tons of information. I could go ahead and see when t is negative 5, I'm at negative 2, negative 6, somewhere down here in the third quadrant. When t is negative 3, I'm at 0, negative 4. So that would complete the third quadrant part. So that's why this one would be quadrant 3. At 0, I'm at 3, negative 1. So I'm already in the fourth quadrant. And it seems like I've moved into the fourth quadrant starting right here at like negative 2 point whatever. At 3, I'm at 0, 2. So now I'm up here. So there's been a lot of stuff that's happened in between. So somewhere in here I should have plugged in a few more values like my 1 and my 2 in my table, and that would have given me a bit more information. But somewhere in there I would have had my quadrant 4. I would have moved somewhere in there to my quadrant 1, I believe, to get up to here. And then I'm at negative 2, 4. So right here is my quadrant 2. And this hit my quadrant 4 and quadrant 1. So what I would need to do is just be a little more careful and check out what's going on right here as to where the split actually happened. But if you notice as I'm graphing, it's like, oh, I got to the end, and then somehow, oh, I got to the end. Then somehow, oh, I got to the end. So I would have graphed it in pieces, and those pieces would have kind of told you what the intervals are. Does that kind of make sense? All right, the rest of you guys, you had your chance. So in 5 seconds, I am transitioning to polar. 5, 4, unless I see a hand telling me to stop. 3, 2, 1. Section 11.3, here we go. Section 11.3, here we go. As you guys get back to notes, we were doing this yesterday, the conversions using the right triangle. I'm going to go ahead and zoom in real fast on our examples that we're going to start today off with and see how we do. We're doing just some coordinate conversions, which are point conversions. So the first one is a rectangular point, aka an xy, trying to get to polar points, r thetas. And the second one is starting from r thetas, trying to get to xy's. So let me go ahead and make this a little bit bigger for you. And I want you guys, you're allowed to collaborate in your groups using the formulas from yesterday. Ready, set, convert. You have x's and y's getting r's thetas, or you have r's thetas getting x's and y's. Dean and Gavin, make sure I check your covered textbook and expo marker. All right, here we go. We are given the point, negative 3, 3, which is an x and a y, and we need an r and a theta. My easiest way of doing it from my head anyway is to go negative 3, to go positive 3, and say third quadrant. And then you can go ahead and do r just by doing Pythagorean theorem, which would end up being r is equal to the square root of 18, yeah? Which is the same thing as 3 rad 2. You guys agree? And then theta opposite and the adjacent are the same? What kind of angle would have opposites and adjacents that are the same, whose tangents are 45s, but in the second quadrant? So therefore, my theta is 3 pi over 4. You can also do tangent inverse of -1 using your head, not the calculator. So, could the point 3 rad 2 and 3 pi over 4 be valid? But why does it say find two different sets? So y is also -3 rad 2 and -pi over 4. One other coordinate, but there are many. There are infinitely many. How does this go to the exact same location and look so different? What's my angle? But what's a negative radius do? Not go towards the angle, but go away. Oh. What would have been another point that you could have used? 7 pi over 4? With this one? Yeah. You could have gone negative from 7 pi over 4.
Positive 3 or 2 and negative 7 pi over 4.
Ooh. Careful though. It wouldn't have been a negative 7 pi over 4. What would it have been? Negative.
Oh, sorry, 5 pi.
Yeah, negative 5 pi over 4. Because you don't need to go to the first quadrant, you just need to go to the second quadrant. And guys, we haven't even touched yet. Because negative 5 pi over 4 would have put you here in a positive 3 rad 2. We didn't even touch coterminal angles. You could have done 2 pi plus and gone positive. Or 2 pi minus and got, well, we did that actually. But, yeah, how many points could you have put? With coterminal angles, infinitely many. But all of them had to be dealing with 45s. 45s either in the second quadrant and going towards a positive radius, or fourth quadrant and going, not towards, but away with, how do we go away again from an angle? A negative radius. So what's different when you're going from polar to rectangular? If you have an r and a theta, how many answers are there going to be? There's only one x, one y to get to every single location on the xy plane. Polar, you can spin, you can turn, you can forwards, you can backwards to get to the same place many different ways. But going right, right, left, or up, down, there's only one way. So this one, I would have graphed my 4 pi over 2. Oh, hey, that's easy. It's the point 0, 4. I know, I cheated, I graphed it. Are there formulas that could have gotten you there as well? Yeah. Isn't there something snazzy where you set up, well, I guess it would have been hard to visualize. I usually visualize it, but you could have done something with x equals r cosine theta. Just a hint, that's going to be a very important formula to memorize. So x is equal to 4 cosine of pi over 2. Y is equal to r sine theta. So y is equal to 4 sine of pi over 2. Cosine pi over 2 is 0. Anything times 0 is itself. Or sorry, is 0. Sine of pi over 2 is 1. Questions on point conversions or coordinate conversions? Does visualizing help? Yes. I think so. I think so. But is that the only type of conversion that's out there?
No.
Nope. How about equation conversions? Before we get to equation conversions, can we talk about something real fast? Before we talk about equation conversions as far as examples, let's write a couple notes. The polar graph, r equals f of theta, is the curve defined parametrically by x is equal to r cosine theta, y is equal to r sine theta. So we still have that right triangle relationship, which is going to be helpful still. But what are these showing me if x equals r cosine theta, x equals f of theta cosine theta? Y is equal to r sine theta, y is equal to f of theta sine of theta. Yeah, you can define polar curves parametrically by just plugging into x equals r cosine theta, x equals r sine theta. If they give you a polar function, you can technically go parametrically to get x's and y's. So there's a pair of equations. But we would need to make it by plugging in to a formula. Which in chapter 11 is going to be necessary multiple times. To find x, to find y, you're going to have to get or know to plug into r cosine theta or phi sine. Polar to rectangular. Polar to rectangular. What if I was to give you r is equal to, given the equation, using all the relationships of a right triangle that we wrote down earlier, or using what's right up above. How can I get that equation into x's and y's? How can I get that equation into x's and y's? Ooh. R squared equals x squared plus y squared? Okay, what would happen if we did use that one? So I've pretty much given you like tons of different formulas that you might use. So we heard one, let's try it. So x squared plus y squared. We have x's, we have y's equals r squared. Huh? Well, we gotta get rid of the r to get to an xy equation. So 16 sine squared. Now what? The r's gone, that's great. But what else do we still need gone too? Theta. But theta's stuck where? In a sine, and sine's being squared. So I could get rid of this if I could just figure out who sine of theta is, right? Wait a minute, what's sine of theta? Opposite? Over? SOHCAHTOA. Tangent is opposite over adjacent. Opposite over hypotenuse. Oh, so I can replace sine of theta with y over r. Wait a minute, if I was replacing sine of theta with y over r, maybe I should have done that way back here before, well, okay, there's lots of different methods to doing this. Someone saw this formula, we said, cool, x squared plus y squared is throw in r squared. Now we gotta deal with that. Who's sine? Okay, there it is. But, okay, theta went away, but who's back? R. Okay, but don't we know what to do with r squared? X squared plus y squared is equal to 16y squared all over r squared. What can we do with r squared? Yeah, back to that formula again. So 16y squared all over x squared plus y squared is equal to x squared plus y squared. Do we technically have an equation with x's and y's? Yeah. Is it necessarily the simplest form? Could we stick it to the main? Well, I guess we could pretty quickly. Are you going to have to somehow make it magical, kids? But you're used to that, yeah. I guess you could FOIL, you could simplify, you could do all sorts of things. The other way you could have gone, kind of show an alternate route. I'm not saying it's better, I'm just saying it's alternate. I think I would have gone ahead and done r is equal to 4 times. I would have thought of sine by going up above. Sine is y over r. I probably then would have moved this to the other side. R squared is equal to 4y. And then I would have plugged in x squared plus y squared is equal to 4y. Wait, that's different than... This is just the square root of that. We went about it a little bit harder way. Still work. Still valid. These are the exact same thing. this one ended up with the squared version of that one. Same thing, just a little bit different version. But that looks a lot different than that. Kevin?
Couldn't it be 16x squared also? Because we got y over r based on the triangle.
But remember, the triangle is based on how rectangular coordinates are graphed, so we can't actually flip those. Does that make sense? Yeah. And we're dealing with a theta that's not being measured out here, it's measured from the angle of inclination. But good question, though. If it was something like physics where we were just randomly, then we would be in trouble. But since it's very specific to graphing. Yeah. Okay, so how about, wait, another polar to, oh, polar to parametric. Ooh. What if we were to do the exact same equation? How can we get parametric equations? So we don't need y equals f of x, or we don't need an equation, an implicit equation, which is what we ultimately did. In terms of x's and y's, we just need a parametric set of equations. So given r is equal to 4 sine of theta, what could we do with this? You just wrote a note about parametrically defined equations. What did that note say to do? John started saying these formulas that we've already talked about, x equals r cosine and y equals r sine of theta. What did you keep saying, John? You said x equals r cosine theta, so?
F of theta cosine theta.
So we can say x is equal to who r is times cosine. And y we can say is who r is, just a quick substitution, times sine. Well, that's a bit easier. Parametrically defining, we can say, well, we have an expression for x and an expression for y. We just need it in terms of theta, so substitute in what r is as a function, and you're done. Which might not seem very useful at this point, but if they were to say something like, in a future AP problem, what is the slope of the curve, or the slope of the path that a particle is on when t, let's say it's in terms of t and not in terms of theta, that could be a lot more exciting. When theta, or when t is equal to pi over 4. Do you want this type of equation if you're trying to plug in theta, or the parameter, when you're trying to plug in for the slope of the tangent line? I mean, taking a derivative we could totally do, even the one up above we could totally do, but if they give us t is equal to, or theta is equal to, how do we plug it in? We don't even have a theta. So this one says, oh, you have a theta, but how would you do a tangent line? Maybe a him prime over a him prime? Forgot we haven't talked about that yet, just kidding. That would be a good way to do it. You could do dy dx in terms of a third variable t, or in terms of a third variable theta. And that could kind of save you some time, and the direction of the question might kind of point you that way anyway. Okay, what did we not do? We didn't take a rectangular equation and make it polar, because there strictly just isn't any point. I mean, it might show up in your homework, but a polar equation is the one you're less familiar with. Converting that to rectangular converts it to something you're more familiar with, which is helpful. Going the opposite direction isn't very helpful. So let's talk about how we're not familiar with polar. Since we're not familiar with polar, if you were given this function, and if in some way, shape, or form you needed to visualize it without a calculator, what would you do? Oh, that's the number 1. Sorry, example 1. For graphing. Good question. Could be a P5 problem.
Start plugging in stuff.
Yep. But I would plug in the same way you guys did in homework last night with parametric stuff, right? Well, some parametric ones you had last night had trig. What kind of tables did you guys make when they had trig? radians and unit circle. So, let's be strategic. Could we plug in every single angle around the unit circle? Yes, but I didn't make room. You could. And if you did, it might be very helpful to know the decimal approximation for square root of 1. Oh, that's easy. 1. Square root of 2. Square root of 3. Square root of 4. I know that one. Because unless you know a decimal approximation, how are you going to graph the points for root 3 over 2 or root 2 over 2? If you weren't supposed to use your calculator, better turn into Mrs. Leon. Anyway, so we're going to try to avoid the radical dudes. But then if worse comes to worse, it might be a good idea to have some decimal approximations to at least get some in-between points. So to avoid the radical dudes, hey guys, what function is this R built on? What function? The theta, but the theta is inside who? Cosine. When is cosine really nice? At pi over 3's. Why? Because cosines of pi over 3's are 1/2s, not root 2 over 2's and not root 3 over 2's, the nasty decimals, but 1/2s. 1.5. So what I'm going to do is all of the 0's and 90's and the pi over 3 dudes, because the pi over 3 dudes I know how to graph, at least approximately. So then if I was to plug and chug, using my unit circle knowledge, of cosine being 1 at 0, 2 minus 2 would be 0. Of cosine being 1/2 at pi over 3, 2 minus 1/2 times 2 is 1, 2 minus 1 is 1. Of cosine being 0, 2 minus 0 is 2. Of cosine being negative 1/2, 2 minus negative 1 is 2 plus 1. Of cosine being negative 1, well, 2 minus a negative 2 is plus 2. 2 plus 2 is 4. Negative 1/2. 0, 1/2, 1. And I've ran the full gamut. I'm going to need my pi over 3's in the first and third and the fourth and second. I'm going to need to be able to go out to 1, 2, 3, and 4 as I go around. So I'm going to make 4 my maximum radius in all my units. And I'm going to go around graphing. So I'm going to start at 0, 0. I'm going to move to pi over 3 with a radius of 1. Pi over 2 with a radius of 2. 2 pi over 3 with a radius of 1, 2, 3. And then a radius of 4. And then a radius of 3. Radius of 2. A radius of 1. Radius of 0. Do you guys remember these dudes called limasomes? And this is one with a cusp. In pre-cal, well, I think we kind of memorized stuff with limasomes. A plus B sine or cosine of theta when A is bigger than B, or A is equal to B, or A is less than B. Certain things happen, like little baby inner loops or little baby cusps, or maybe it just goes flat. With cosine, we have a certain symmetry because of how the unit circle values repeat. With sine, we have another type of symmetry. Could you memorize all the polar graphs again? Or maybe for the first time? Yes. And it might be helpful eventually in chapter 11. But what's a good skill I want you to develop now? Using a table in the unit circle and being strategic and seeing if you can get it. Now, let me peek real fast, because time is running short. And what else we have? Oh, another graphing example. Oh, and then we're done. Okay, so you guys bust them out. Who's this dude? Give you a 30-second head start. Ready, I'm warming up. I'm throwing pitches off to the side just to be able to see. Section 11.3 tomorrow. Oh, I didn't write it on the board. You are still accountable. It's in your Google Classroom. I'm putting it in now. But it wasn't before.
I do every day.
I'm assigning it in Google Classroom as you leave.
Are you gonna be in here during lunch?
Yes.
Alright, then I'll just leave. So
Okay. Post a comment. I'm being nice the first couple weeks.
Is this one I do tomorrow?